Thank you. I guess when I started studying political science, I never really figured that I'd end up being a spin doctor, but that's sort of how it ended up. So thank you, Chun and Alan, for the introductions. So I'm Darío Arena from Photon Sciences Directorate. I do my work at the National Synchrotron Light Source. So here's a picture of the NSLS in springtime, and if you were to go inside, you would see that the NSLS currently operates two what are called storage rings or synchrotrons. The larger one is the X-ray ring. The smaller one is the VUV ring, VUV and infrared ring, and that's where our beamline is located, beamline U4B. So you're welcome to stop by and talk to me if you have any interest afterwards. So here's an outline of my talk. I'll give you an overview of magnets. I'll talk very briefly about magnets and energies, and then how it can address some of the energy issues. Talk a little bit about the origins of magnetism in materials, in particular a concept known as angular momentum, and how we can use X-ray spectroscopy to look at magnetic materials, and how we can use X-ray spectroscopy to investigate high-speed dynamics. And I'll explain why that's important. And at the end, if there's time, I'll briefly talk about some future work that we're planning related to the ARPA-E thing. Well, my fascination with magnets probably started from spending too much time watching Saturday morning cartoons. This gentleman here, Wile E. Coyote, would always find interesting ways of using magnets, which often ended up with him getting hit with an anvil in the head. That hasn't been the case with me so far, but I would like to make the point that magnets are among the oldest technological materials that we have with us. So there's written records as far back as 600 BC of lodestone, a naturally occurring kind of magnet, an iron oxide. Compasses were used in China for divination purposes as early as 200 BC. And there's some very intriguing hints that something very much like a compass may have been used in Mexico by the Olmec people as early as 1000 BC. This is a picture of a piece of lodestone that's been polished in such a way that the archaeologists think that it might have been used for sort of like a compass. However, most of us think of magnets in a completely different way, in something like this. It's the things that we use to organize our life on our refrigerator. So we would use magnets to stick up pictures of our families, put up calendars, notices, and so forth. However, I would like to make the point that magnets are really ubiquitous, and we really can't get away from them. If you look at anyone's desk, especially one that's much neater than mine, you would see that magnets occur in speakers and headphones. They're indispensable for wireless technologies, which is a huge growing area. And, of course, they're used in magnetic hard drives. And so I'd like to talk a little bit about magnetic hard drives. So let's go back to Wile E. Coyote. And his horseshoe magnet consists of a north pole and a south pole. And if you were to take this little horseshoe magnet and kind of open it up, you would have a bar magnet that also has these north and south poles. And in the center here, we have an arrow indicating the direction of the magnetism, the magnetization inside this bar magnets. Common magnets are referred to as ferromagnets, and I'll use the abbreviation FM throughout the talk. So getting back to disk drives are really an amazing piece of technology. What's shown here is kind of an artist's conception of a disk drive. This is a platter that would spin around at a tremendous velocity. Some of the best disk drives spin around at 7,200 revolutions per minute. What makes these things work is at the end of this device called a slider. At the end of the slider, if you blow that up very much, you see something here, which is a read head, and then if you blow that little area up even further, you see something similar to this structure. And what this is an assembly of thin layers of different kinds of metals, a ferromagnetic layer, a non-magnetic layer, and then another ferromagnetic layer, typically referred to as a soft layer and a hard layer, and I'll explain what that is further on. But these are really, really thin layers. So typically the magnetic layers are on the order of 5 to 10 nanometers in thickness. This non-magnetic spacer layer might be 1 to 2 nanometers thick. And just as a reminder, a nanometer is 10 to the minus 9th meters. And a strand of spider silk, for comparison, is about 5 times 10 to the minus 6. So these structures are a factor of 1,000 smaller than the width of spider silk. So these are really ultra-thin films. And they're typically grown for the hard disk industry on platters that are, several inches across by techniques called physical vapor deposition, more specifically a technique called sputtering. All right, so the thing that has made hard disk drives advance so quickly is the discovery of an effect called giant magnetoresistance, or GMR, discovered in '88 and applied in '98. In things like hard drives. So if you have two of these, well, let's say you have one of these systems, you can have an orientation of the magnetism in the two layers that is parallel. It gives you a low resistance state, which would give you a binary 0. If they're anti-parallel, you would have a high resistance state, and that would give you your binary 1, for example. And this application of GMR has really led to a huge increase in what's called the areal density of hard disks. So the ability to pack information, more and more information, into a hard disk that's trending up now to several hundred gigabits per centimeter squared, up there it is, and it's trending up to a terabit per centimeter squared. And so again, just to remind you, the thing that's allowed that to happen is the read head, which is at the end of this slider, that takes advantage of this GMR effect. And it was an important discovery that was recognized in 2007 by the Nobel Committee, which awarded the Nobel Prize to Albert Fert and Peter Grunberg. So as I mentioned, magnets are ubiquitous. You really can't get away from them, and they have applications across a tremendous range of industries and technologies, from generating power, transportation, biomedical, magnetic sensors, wireless microwave devices, information technology, and new areas such as spintronics and nanomagnetism. I'm going to focus in this talk on issues that relate primarily to information technology, read heads, and non-volatile memories. At the end, if I have a little bit of time, I'll talk about this ARPA-E project that we've gotten involved with, looking at power generation or magnets that have applications in these two areas. Okay, so back to Wile E. Coyote. What's going on inside these magnets? I use the terms sort of magnetism and magnetization kind of loosely. So now let's take a look inside these magnets. And if you were to do that, many of you might recognize this picture. It's a little hard to see, so let me just bring out the contrast a bit. This is a picture taken from a standard introductory solid-state physics textbook. It shows what's called the magnetic domain structure in a crystal of nickel called a whisker that's about 50 microns across. And inside this piece of nickel, you have these domains. Inside each domain is an area that acts like a little tiny mini bar magnet. And so it has a well-defined magnetization direction. But if you average all of this out, the net moment, the net magnetization across the entire sample can be 0. Incidentally, these domains are also the things that can be used to store information. Let me talk a little bit more about domains and hysteresis, and I'll sort of motivate that by asking, what if a magnet was like a spring? What do I mean by that? Well, if it behaved like a spring, then I would have something called the magnetic strength, or the magnetization, and here I would have an externally applied magnetic field. This would be a very poor magnet. So if you wanted to hold something on your refrigerator with this kind of magnet, it would never work, because you'd have to apply a field in order to get this thing to hold anything. And when you took that field away, things would just fall down. Magnets are not like springs. They don't behave like springs. They have a property called hysteresis. And what that means is that if I apply a magnetic field strong enough, when I take that magnetic field away, this measurement of magnetic strength doesn't drop back down to 0. The reason it doesn't drop back down to 0 is related to this domain structure that I mentioned. What's shown here are sort of different magnetic domain patterns that occur as I apply a magnetic field. So I'm increasing the magnetic field as I go from top to bottom. And these magnetic domain patterns, what tends to happen is that if I have a magnetic field pointing in this direction, then the domains that are aligned with this field tend to grow, and the other ones get shrunk out until you have squeezed out all the other domains, and you get what's known as a single domain state. And now when I take the magnetic field off, you might not go back to the original state. You might end up in one of these intermediate points where there's still a considerable net magnetization in the direction in which you applied your field. And so I can describe some of these processes, average processes for a magnet, by these quantities m sub s, the saturation, which measures how much magnetic moment that I have in my sample, how strong is the magnet. Remnants would be the amount of that magnetic moment which is left after I take the field away. And then the hardness or coercivity is a measure of how difficult it is for the magnet to switch. How much magnetic field do I need to apply to get this thing to reverse? And just as a reminder, this is a little schematic of one of these bar magnets. We're all sitting on a giant bar magnet, which is the Earth, and the Earth has a magnetic field. So let me talk about some standard magnetic fields that we might be exposed to. The Earth's magnetic field is about 30 microtesla. So that's sort of the preferred unit of magnetic measurement these days. There's sort of an older unit called Ørsteds, which is used quite a bit still. The switching field required to switch one of these GMR reed heads that I mentioned earlier is about 0.4 millitesla, about half a millitesla, or for Ørsteds. One of these flexible refrigerator magnets that are handed out as freebies is about 5 millitesla, or 50 Ørsteds. One of these very, very strong super magnets is about 1.25 Tesla. And if you've ever had a an imaging procedure involving an MRI, you've been exposed to a field of about 1.5 to 3 Tesla. So how can magnets help with the energy issue? Well, there are many potential applications. I'll focus on one that's related to what I'll talk about a little bit later, which is the power consumption increase in computer chips. So as we all know, computer chips have had a tremendous growth in their capabilities over the past 4 or 5 decades or so, but that comes as a price. So as you make your transistors in a computer chip smaller and smaller and pack more and more of them into a chip, the active power goes up considerably, and it's sort of over 100 watts now or thereabouts. However, the standby power is growing at an even more rapid pace. And the standby power is the power which is consumed by your computer if it's just sitting there doing nothing. It's the power that's required to maintain the information in the computer, and it's a result of what's called the leakage current. As you make your transistors smaller and smaller, a little bit of the current sort of sneaks around, and you have to keep supplying this over and over again. Otherwise, you lose the information that's on your computer. So how can magnets help to eliminate this or reduce this? There's a kind of new memory architecture that's being developed called MRAM, which is an example of non-volatile memory. And that means it's a memory that I can take the power away, and the information which is stored won't go away. So as an illustration of that, I have these layers, again, these 2 ferromagnetic layers in this low resistance state, which can be my binary 0. I can apply a magnetic field. One of the layers switches, and now I have my number 1 state, my binary 1. I can apply the field in the other direction. It switches again. And again, I go back to my 0 point. And this now becomes a memory element. And this is not just sort of vaporware. There are companies that have started up recently that have developed and started marketing this magnetic random access memory, or MRAM, technology. This is going to be hard for you to read. This is from their data brochure. This is a company, Everspin, which is out in Arizona. Let me highlight this bullet point. So they say here, data is always retained for greater than 20 years without backup cycle or batteries. So you could put some information onto one of these chips, turn the power off, walk away for 20 years, come back, turn the power on, and it would be in the same state that you had it to begin with. Okay, so let me switch gears for a moment and talk a little bit about angular momentum, which is the source of magnetic moments in materials. And I'll motivate that with talking about gyroscopes and bicycle wheels. So this gentleman is spinning up just a common bicycle wheel, putting it on its side, and then it does something really remarkable. It experiences something called precession. So it rotates around. And it rotates around because the bicycle wheel now has a property called angular momentum. And that's related to the spinning of the bicycle wheel. And you'll notice if you pay attention that the bicycle wheel is, the rotation speed is slowing down. And that's due to the friction inside the bearings of the wheel and also friction from the string over here. And as the bicycle wheel slows down, the precession axis or the angular momentum axis drops lower and lower and lower, and eventually it's going to be aligned with gravity pointing down. And so friction causes the system to lose angular momentum, which allows it to point in the direction of gravity. So here's just a frame from one of the frames from the movie, and if I sort of stylize this a little bit, I can illustrate what I mean by angular momentum and the direction of the angular momentum. I can use what's referred to as the right-hand rule. So if the bicycle wheel is rotating in this direction, again, curl my fingers around the direction of the rotation, and my thumb now points in the direction of the angular momentum. Now, I mentioned that this thing was precessing around, and it was precessing around because of the effect of gravity, which exerts a torque, which is an analog of a force, and that is what causes the angular momentum to sort of precess around. Now, in materials, in what we call ferromagnets, or in any material, the angular momentum is not carried by bicycle wheels, obviously, but it's carried by the electrons in the material. And there are two types of angular momenta associated with electrons. The first one is called the spin angular momentum, or the spin moment, and it's really an intrinsic property of the electron. You can kind of think of it as the angular momentum associated with the top spinning around. It's not an imperfect picture, but it's a good model. And so by the right-hand rule, I can say that if the top is spinning in one direction, I would have angular momentum pointing up. If I switch it now to point and it's rotating in the opposite direction, the spin moment would be pointing in the opposite direction. In addition to the spin moment, I can have an orbital moment, and that orbital moment arises because of the motion of the electron around its nucleus, and just sort of kind of in a hand-waving sort of argument, as the electron orbits around, I have an additional source of angular momentum called the orbital moment, given the symbol L. The spin moment is S, and the total angular momentum is L plus S, and given the symbol J. Okay, so we have magnetic materials. How do we go about investigating them? Magnetic materials can have a very wide range of properties, but there's still room for improvement, which is why it's still a considerable active area of research. But their composition is non-trivial. They can be alloys, intermetallics, oxides with different oxidation states of the ions inside of it. And as I showed you with the GMR structures, they can have these ultra-thin structures. So we want to be able to investigate these in detail. And what we're going to use is a technique or a class of techniques called spectroscopy. There's various ways of describing spectroscopy. I'm going to take a very broad approach and say that it's just a method of resolving the interaction of light or other forms of energy with matter. And just to sort of motivate this a bit, we're all kind of spectroscopists in a way. Our eyes are spectroscopic instruments, and so we can look at the different colors in the rainbow over here that's produced when I send white light into this prism, so our eyes are able to resolve these different colors. But going beyond that, we're also all atomic spectroscopists, because we've seen signs like this. And this is sort of imperfectly called a neon sign. It's really a gas, I think a gas discharge lamp or something like that. The different gases inside emit at different colors. And so here are the colors that would be emitted for helium, neon, argon, krypton, xenon, the noble gases. And so these excited atoms inside these lamps can emit light. When they do that, they emit color, and that color can be used to identify the atomic species. And energy is the generalization of color. And so spectroscopy involves both looking at the emission of light, as in the case of these neon-type lamps, and also the absorption of light. And the absorption of light is what I'll focus on. Now, before talking about X-ray absorption, I just want to mention atomic core levels. And so if you think about kind of the model of the atom that we all learned about in high school, you have a positively charged nucleus and then negatively charged electrons zipping around that nucleus in their different orbits, or more precisely, their orbitals. And those electrons can be held on by the nucleus to a greater or lesser extent. They can be bound to the nucleus, and they can be bound with different energies. So this is sort of referred to as binding energy, which is the energy required to remove an electron from one of these core levels and eject it from the material. I'm going to talk primarily about these two core levels, labeled the 2p3 halves and 2p1 half core level, which are relevant for looking at magnetic materials, many magnetic materials. I'll also talk a little bit about the valence band, and the valence band arises from the outermost electrons in an atom. These are electrons which are the least tightly bound, and which participate in the chemical bonding, which gives us, which produces crystalline structures that generate solid-state materials. And that valence band can be filled up with electrons up to a certain level. You may have orbitals available above that, but there are not enough electrons to populate them. Okay, so let me just move forward. So the binding energy of these electrons can be used to identify the atomic species. So here are the binding energies for these 2p3 halves and 2p1 half levels. For iron and nickel, you can sort of read off the numbers there. And we're going to do a very simple experiment. We're going to take a nickel-iron alloy sample. We're going to have some X-rays incident on it. We're going to have some X-rays transmitted through the sample. The remainder are the ones that are absorbed inside the sample. We'll vary the energy of the incident X-rays, and we'll measure the intensity of the X-rays which are transmitted. And so what we're really doing is we're taking an X-ray and tuning its energy so that it sort of coincides with one of these core levels. That excites one of the electrons from these core levels to these available states in the valence band. And it's sort of like having someone move from the ground floor here in Berkner up to the balcony. That can only happen if there are seats available up in the balcony. If the seats are all full, then this transition can't occur. And by doing that and varying our incident photon energy, we can record these spectra that allow us to identify, in this case, iron and nickel and these different core levels in this sample. And it aligns very well with the energies that we would expect based on the binding energies. Now, we do these measurements with a very specific X-ray source, and the X-ray source which we use is a synchrotron, as you might guess. And here's kind of a nice little animation of a synchrotron which you can download. It's from a small synchrotron in Denmark called Astrid. And this is the synchrotron. Here's the electron source, which generates electrons. It's called a microtron. And it inserts electrons into the synchrotron, also called a storage ring. There are 4 magnets in this particular synchrotron called bending magnets, and a cavity which increases the energy of the electrons. As the cavity provides more energies to the electrons start to bunch up, and they keep going through these bending magnets. When they go through the bending magnets, they emit light, and that light can be directed along beamlines, which we use for our experiments. And so many beamlines can be hosted at these synchrotrons. What you'll see in a second is a pulse of light traveling down a beamline over here. It hits a device called a monochromator, which gives it selects out different energies, and then we can use this light for our different kinds of experiments. So this is for an experiment called photoemission. So how do we deal with magnetism? I showed you that we can identify the different elements using X-ray absorption, But to look at magnetism, we have to use polarized light. And we're all familiar with polarized sunglasses. And the reason that polarized sunglasses work is light is an electromagnetic wave that can oscillate, and the electric field vector in that wave can oscillate back and forth. And it can oscillate back and forth in, let's say in this case, a vertical direction or a horizontal direction. And these polarized sunglasses are designed in such a way that they block the light in the horizontal direction, which results in a reduction in glare. And you can have tremendous differences in the photos that you take, in the glare coming off of, let's say, a highway as you drive along by using these polarized sunglasses. We're going to use a very different kind of polarization called circular polarization. Now, instead of the electric field of the photons waving back and forth in one direction, it actually rotates in space. And so now it produces a kind of a corkscrew motion as the photon propagates along in space. And if you see this thing rotating around a little bit, it should remind you of angular momentum. And indeed, the photons now have a well-defined angular momentum. And we use that property to investigate the magnetic materials. So as I mentioned, in the synchrotrons, we have these bending magnets, which are used to produce the X-rays. The photon beam, if I look at that bending magnet and blow it up, it has well-defined polarization along different parts of that photon beam. In the center, the beam is linearly polarized in the horizontal direction. Above and below the plane of the synchrotron, I can get either right circular polarization or left circular polarization. And this is what we use for our experiments. We just use some kind of photon mask or polarization mask to select out the kind of polarization that we want for our experiments. Okay, so putting the circular polarization together with X-ray absorption, we come up with X-ray magnetic circular dichroism, which is a bit of a jawbreaker, so we usually just abbreviate it XMCD. And this is a way of getting element-specific information about magnets. And it's essentially just the differential absorption of circularly polarized X-rays by a magnetic material. So if I have this simple iron-nickel alloy, and I have X-rays which are either polarized with right circular polarization or left circular polarization, I'm going to get some X-rays that are transmitted through, and depending on whether the angular momentum, the magnetization of the light of the sample, is aligned with the angular momentum of the light or anti-aligned, I would get a different amount of X-rays propagating through my sample, transmitted through. And if I toggle back and forth, you can see that's sort of schematically indicated by the number of photons coming out the other side. And so in XMCD, what we do is we collect two spectra in the aligned and anti-aligned configuration, shown here in red and blue, and then we take their difference. And their difference is the XMCD spectrum. So it's really just the difference of these two X-ray absorption spectra depending on the alignment or anti-alignment of the magnetization with the helicity of the light. And so now we have an element-specific method to measure the magnetic properties, because as I mentioned, this is now tied to those elemental core levels, which I can use to identify different elements in my material. And then by doing some further analysis, I can also calculate the contribution from the spin and orbital moments. Now, at U4B, we have a wide range of science programs covering sort of conventional magnetism and this term spintronics. We also look at a lot of oxide materials that have interesting, what are termed correlated electron systems. We've been doing chemical studies, in particular looking at catalysts. And we've looked at ultrafast dynamics at U4B, and I'll explain a little bit how we go about doing that. So our samples for looking at transmission are pretty simple. We grow samples using this sputtering technique, primarily by our collaborators at Columbia University. Recently, we've started making use of the Nano Center here on site. We grow the samples on these silicon nitride membranes, which are very thin. They're about 100 nanometers thick of the thickness is only about 100 nanometers of silicon nitride, and they're essentially transparent to X-rays. And so we can grow these very nice stacks on them. And if we tend to operate in a vertical geometry, we have the X-rays coming in. We have the different layers which we deposited, and we can monitor the intensity with a photodiode. What's shown over here is how we introduce the magnetic excitation into our sample using what's called a coplanar waveguide. So the sample we are going to look at is very reminiscent of one of these GMR-type structures. It has an iron-nickel layer and a cobalt layer separated by a rather thick copper layer. But by so what we can do is collect XMCD spectra at the iron edge, the nickel edge, and the cobalt edge. And then what I can do is tune my photon energy to the maximum XMCD signal for iron, for nickel, or for cobalt, indicated by these arrows. And then I can apply a magnetic field back and forth. So these are static measurements to begin with. Using that, we can develop what are referred to as element-specific hysteresis loops. So these are the same as those hysteresis loops that I talked about earlier, except now we're able to specifically identify the hysteresis associated with this layer, or with which is the iron-nickel layer, or with the cobalt layer. And so if I apply a magnetic field, let's say in the left to right direction, I can pull all the magnetic moments in both the iron-nickel layer and the cobalt layer in the same direction, and that would be up here somewhere. If I switch the direction of the magnetic field, I would drive the system down this way. Eventually, the magnetization would rotate, and I'd end up down here. And so I've gone from a situation where the magnetization in my sample is pointing in one direction, and it's gone through a reversal of 180 degrees or so. And so this gives us a very nice way of calibrating my angle. Another thing to notice is the iron and nickel. If you look at the coercive fields here, the hardness of these systems, this is basically the same, or essentially the same for the iron and the nickel, whereas the cobalt is slightly harder. And this sort of illustrates one of the advantages of XMCD, is that you can really distinguish what's going on in these different layers. All right, now, what does dynamics have to do with any of this? Well, let's say I wanted to use this as a memory element. I don't want to sit around for 20 years, although it's nice to be able to do that. I want to be able to write my information quickly and read it out quickly as well. But there are a couple of issues. There's a first issue associated with what's referred to, So I would be able to just switch these things back and forth and get my zeros and ones out. But then if I have a problem, such as ringing, that would lead to a way of decreasing the potential speed of this system. And what I mean by ringing is that when I try to switch this thing, it doesn't settle down to the other state quickly. Instead, it sort of bounces around. The other issue is what if there's some kind of mutual influence? You really want these layers to be independent to a certain extent, but if I switch one, and now these two things don't end up in perfect alignment or anti-alignment, I can end up with a situation where I'm neither in a 0 condition or a 1 condition, and that would pose problems for these memory-type applications. So the first issue, this ringing, is related to a process called damping, and it's also related to a more fundamental question, which is what causes the magnetization motion to stop? So if you think back to the bicycle wheel example, it was precessing around because of its angular momentum, and it was slowly losing its angular momentum due to friction, and that eventually allowed it to point down into the direction of gravity. But what plays the role of friction in magnetic materials? So if I didn't have friction, all that would happen when I apply a magnetic field is that the magnetization would just rotate around forever. Now, there is something analogous to friction, and we know that because we have sort of empirical evidence for it. If I apply a magnetic field, it will spiral around. The magnetization may spiral around, but it will eventually point in the direction of the applied field. And you can analyze this in various ways. A popular one is using the Landau-Lifshitz-Gilbert equation. And I won't go into the details of it over here, but it's basically broken up into two terms. The first term defines this precession behavior, where the magnetization just rotates around. The second term is this energy loss term, the equivalent of friction. And that is where damping comes in. So that second term is defined by this parameter alpha, which is this energy loss or damping constant. But the issue is that there's some controversy about alpha. And it's essentially, in this application, a phenomenological constant that's thrown in to make the equation work. And there have been many attempts to describe what are the origins of alpha. And the controversy has sort of been going on for a few decades now. So we're going to examine this not by looking at full switching of magnets, but instead by looking at what's termed driven harmonic motion. And an example of this is a mass on a spring, which you may have seen a number of times. You can take a spring, suspend a mass from it, and bounce it up and down. And if I now look at the the position of the mass as it's bobbing up and down relative to its position at rest or its equilibrium position, that position as a function of time will go up and down, follow the sinusoidal form. And I can describe that via its amplitude, its period, how long it takes to complete one cycle. And I can also describe its phase. Where do these peaks occur relative to the time when I start my stopwatch? So the advantage of looking at driven harmonic motion to look at dynamics of magnetization is its simplicity. Another property called linearity, meaning that the deviations are small, and the combination of these things lead to very high precision in our measurements. So the analog of the spring bouncing up and down for magnetization dynamics is that the magnetization precesses around, as I mentioned, and the role of the hand moving up and down is taken by a microwave excitation, which we introduce. So when we introduce this microwave excitation, what happens is that the system starts to precess, and we can now plot the x-coordinate, let's say, of that precession as a function of time, and it sort of undergoes this oscillatory behavior, just like the mass on a spring system. However, the amplitude is not the amplitude of the magnetization moving up and down, but instead the value of this cone angle. And so here's our microwave excitation, and we're going to ask the question, what happens to this cone angle as I apply a magnetic field? So when I apply a low magnetic field, I have a relatively small cone angle. When I apply a larger magnetic field, the cone angle increases and reaches a maximum at a resonant field. And then if I go to a higher field, magnetic field beyond that, the cone angle decreases again. And if I plot that out as a function of applied field, I get this functional form, which is called the Lorentzian. And for technical reasons, we often measure not the cone angle directly, but its derivative with respect to this applied field. But this resonance can be identified as this zero crossing point away from these two peaks over here. Also, the width of the resonance is related to this damping parameter alpha. All right, now one thing to keep in mind is that magnetization dynamics are fast. Typical frequencies occur in the gigahertz range. And just a reminder, 1 gigahertz implies an oscillatory period of 1 nanosecond, or 1 billionth of a second. Now, we know that XMCD is a useful technique to look at different elements in a sample, but how do we look at the ultrafast motion? So we're going to take advantage of a strobe effect, and just as a very fast strobe light can capture a bullet ripping through a playing card, we can also use a similar effect. And if you have multiple shots, you can also pull out detailed analysis of very complicated motion, such as this guy trying to hit a golf ball. Now, in typical flash photography, the time scale is measured in milliseconds, maybe microseconds. We want to look at nanosecond dynamics and faster. So here's our strobe light again. What we're going to use instead of a flash are the X-ray bunches from the synchrotron. So let me skip to that. The width of the bunches at the synchrotron is about 70 picoseconds at the advanced photon source in comparison to the 1 nanosecond bunches here at the NSLS. And that was really the only reason that the main reason that we started doing these measurements out at Argonne. Now, I can vary the delay time between the arrival of these photon pulses and my microwave excitation. And if I do that, what happens is I can then sort of map out if my system tracks the oscillations in my microwave excitation. This is just a simplified schematic of the electronics which we use. We have ways of generating what it's called a phase-locked excitation that is synchronized with the X-ray bunches. And this is the apparatus that we put together to measure this. So it's relatively small. It's only about 10 inches from here to here, 2.5 inches across. It was designed to do 3 things. It had to provide a vertical magnetic field that's provided by these 2 small magnets, a horizontal magnetic field from this little magnet and yoke system, and it also had to deliver our microwave excitation. And so we have a little coaxial waveguide in the center here. And it was designed to be small so that we can transport it to different synchrotrons. Now, does this work? And the answer is yes, it works very nicely. What I'm showing over here is the response of a single iron-nickel layer when we excite it with microwaves of 2.3 gigahertz near the resonance condition. Here's the delay, which I'm increasing. And you can see the response of the system. It follows this very nice oscillatory pattern, both for iron shown in red and nickel shown in blue. And so the 2 moments kind of process together. You'd expect that in a single layer because the coupling, the connection between the iron and the nickel is very strong inside a single layer. Because we have a nice simple sinusoid, we can pull out the amplitude and the phase with very high precision. So we can measure the amplitude with a precision of better of 1/10 of a degree and phase of less than 5 picoseconds compared to the bunch width, which is about 70 picoseconds. So we're doing better than a factor of 10 over the bunch width of the X-rays. And this is small angle motion. This maximum amplitude is a degree or less. So we're in this linear regime that I mentioned. Now, in this more complicated tri-layer sample, I have this iron-nickel layer and a cobalt layer, and I can measure this resonance curve here. And what I see is that I have a main resonance here at high field and a weaker resonance here at lower field. And so I'll call this the high field and the low field resonance. We're going to take timing measurements at the points indicated by the X's, which I'll also give numbers going from low field up to high field. Now, these low field and high field resonances, I can bring them back to the lab, or actually our collaborator measured these at Columbia University using a technique called ferromagnetic resonance, which you can measure at more frequencies and was accessible at the synchrotron. And what's shown here are that high field resonance in red and the low field resonance in blue as a function of frequency. And in addition to that, I've plotted 2 lines, a solid line and a dashed line. The solid line is an analysis of these 2 modes, assuming that there's no connection between the 2 layers, whereas the dashed line assumes that there's some weak connection or weak coupling between the 2 layers. And if you can't see much of a difference between those 2, that's the point. Using this technique over the range that's limited by the data, it's very difficult to tell whether we have coupled or independent layers. All right, so I'm going to go back and use XMCD and tune to these different photon energies so I can see what's going on in this bottom iron-nickel layer or in the cobalt layer. And these are the data which we collect. So here are the various field points, 1, 2, 3, 4, 5, 6. The bottom one shows the response of the iron-nickel layer. The top one shows the response of the cobalt layer. And you can see that they have very different behavior. As I increase the magnetic field, the iron-nickel layer has an amplitude that grows considerably, and it has a rather large phase shift. And the cobalt layer starts off with a relatively large amplitude, but then it decreases and has a much smaller phase shift. I can replot those data to kind of highlight some of these things. This is the low field data taken at 0.1 over here. This is the high field data taken at 0.5, close to this second resonance. And you can see the response for cobalt and iron. Initially, they both have a relatively large amplitude, and they're precessing not quite, but close to antiphase with respect to one another. But as I go to the higher field condition, the cobalt has a much lower amplitude, whereas the amplitude of the iron and the nickel has increased quite a bit. Here's the phase shift for iron and a much smaller phase shift for cobalt. Now, because these are nice, simple sinusoids, I can fit them again with a high degree of precision and pull out the oscillation phase shown up here. The red dots are for the iron-nickel layer, the blue is for the cobalt, and I can also pull out the amplitude as a function of the applied field. And again, we're dealing with very small angle excursions, but less than 1.5 degrees. Our errors are on the order of 1/10 of a degree or less. You can see that the iron has a very large phase shift. You get a much smaller change for the cobalt. And our phase errors are, again, on the order of 2 picoseconds, which is, again, much, much shorter than the bunch width at the synchrotron. Now, we can analyze these, again, to see whether there's some coupling between these layers or not. If we first assume that there's no connection between the iron and nickel layer, we don't do a very good job of describing the data. We do a reasonable job for the phase of the iron, but the cobalt is completely off. We overestimate the resonant field over here for the iron, and we're consistently above the measured amplitude for the cobalt. If we assume a weak amount of connection or coupling between these two layers, I do a much better job of describing the data. So I get the phase of the iron better. I can even get a little bit of this uptick in the cobalt, which we measured. We do a much better job of describing the cobalt and also the iron amplitude as a function of field. And so, to my view, this is a much more transparent way of indicating that you do have some degree of connection or coupling between these two layers than in the earlier measurements which I showed you using just sort of laboratory-based techniques. I can do something a little bit further, and now I can fix my magnetic field right at that resonance where I get the largest angle and sweep out my photon energy now at different points in the oscillation cycle. When I do that, I collect essentially XMCD spectra, or I do collect XMCD spectra, but now as a function of this precession cycle. So these are picosecond resolved XMCD spectra. And this is a particularly important development in addressing this question of damping, because from these spectra, if I can collect them with a little bit better signal-to-noise ratio, I can try to analyze the contributions from the spin and orbital moments, which may tell me something about how damping behaves in these materials. Okay, so to summarize this portion of the talk, we developed a new technique for examining dynamics with X-rays, and it allows us to do spectroscopy at picosecond timescales. I should mention that the technique has been adopted at quite a few synchrotrons, including all of the major ones in the US and several in Europe. The technique enables really precise measurements, again with picosecond time resolution. We can record the full dynamic orbit for the different elements in a complicated material, both the phase and the amplitude, and we can use this information to reveal some subtle interactions that may be masked in sort of conventional measurements. And we hope to use this to address these long-standing controversies on what are the origins of damping. All right, so let me change gears one last time and talk about rare earth permanent magnets. So these are the magnets that you would find down here containing samarium cobalt, that would be samarium cobalt, or neodymium iron boron, which contain these rare earth or lanthanide materials. These are very important materials for green technologies. They are used to produce very strong electric motors and energy recovery systems in hybrid electric vehicles and in clean power generation, such as windmills. If you kind of focus up here a little bit, you can see that these are really large installations. Here's a guy doing some servicing on one of the, probably the gearbox with one of these things. If we can develop new materials that are cheaper and lighter, but still have the same performance of the magnets that are used inside these generators and electric motors, we can make these things more affordable and also adopted more quickly. But there is a problem in that there's a difficulty in obtaining some of these materials, particularly what are referred to as the heavy rare earths, neodymium, dysprosium, and terbium. Over the long haul, it's going to be difficult to obtain these materials, and these are exactly the materials which are of very high importance to this clean energy. So for that reason, we got together with a group of other institutions and a few companies as well to participate in this REACT program, which is Rare Earth Alternatives in Critical Technologies. This is a program sponsored by ARPA-E that Chun mentioned. And what we're trying to do is develop substitutes for rare earth permanent magnets that have zero rare earth content. And so I won't go into great detail on this. I'll just say that we were lucky enough to be rewarded a contract from ARPA-E on this. And our role is to investigate a new class of materials based on cobalt carbide nanoparticles and analyze them in detail with X-ray spectroscopy, in particular to look at what is the role of the orbital moment in establishing a behavior in these materials that mimics these rare earth permanent magnets. So it's going to include some funds to purchase a new end station for NSLS that will be transferable to NSLS2. Now, of course, we're all very much looking forward to using NSLS2, and the reason is sort of given in this graph over here. Here are what are called the brightness curves for some of the standard sources for X-rays at NSLS2, the advanced photon source in green and the advanced light source in red. And you can see that NSLS2 will have a tremendous advantage. These are factors of 10 on the scale over here. And so this increase in brightness will enable us to produce really small beams at NSLS2, which will be looking for, useful for looking at small samples, like those nanoparticles that we get. Not that we'll look at individual nanoparticles, but the original amount of material that we tend to get is very small to begin with. And it would also allow us to have a more powerful microwave excitation, because we can reduce the size of our sample, which would allow us to look at interesting nonlinear effects. So going beyond this linear approximation or excitation that we've been using. So with that, I'll just put up a very broad summary. I hope I've been able to show that by using soft X-ray spectroscopy, we can have a very useful tool for looking at complex materials. We have an active ongoing research program at NSLS, and we've been using these tools to look at this ultrafast magnetization dynamics with this XMCD technique, and we're really looking forward to using these techniques at NSLS2. With that, I'll just like to put up my acknowledgments. I've been fortunate to work here at NSLS and Photon Sciences with Elio Vescovo on the magnetization dynamics work, and also more recently with postdoc Peter Warnicki. This was a close collaboration with the group of Professor William Bailey at Columbia University and his graduate students. And we've recently started doing these kinds of measurements with a group from Scandinavia at Uppsala University and NTNU in Norway. So, of course, I'd also like to acknowledge the DOE for providing the funds for doing these kinds of measurements, and thank you for your attention.
Thank you for a very interesting presentation. We have time for a few questions. Yes.
What is the current feeling about the mechanisms of relaxation in these systems?
So in metals, the current understanding, the best understanding to my knowledge, is what's called the breathing Fermi surface model, where the Fermi surface in these materials is not a sphere, but rather has pockets in there. And because of the coupling between the spin moment and the orbital moment, as the magnetization rotates around, it sort of samples these pockets differently, and the orbital moment then acts as kind of a drag on the spin moment. So what we would like to be able to see, if we can get the right samples, is when we do these picosecond resolved spectra, is to see whether the ratio between the orbital moment and the spin moment remains the same as we go through the oscillation. In other kinds of materials, like oxides in particular, then there are other mechanisms that come into play, things like valence exchange, if you have more than one oxidation state. So you can have electron hopping between different sites. I didn't mention it, but XMCD is a really wonderful technique to look at especially those kinds of materials, because you can identify different valence states and also different crystal field symmetries. So if ions are sitting in octahedral or tetrahedral sites, and if we can identify phase delays between those, that would also go a long way into discussing some of these old but still useful models of relaxation. It's probably more than you wanted to know on that.
Other questions? Okay, I have one. So on the this non-magnetic material, the thin layer between, I guess, iron and other magnetic materials. So what is the material there, and did you try to maybe vary the spacing, the thickness of that layer to get information, additional information?
So the material that I presented was just copper. We are starting a program now where we're looking at different materials that can vary the thickness, in particular things that would have coupling that goes from ferromagnetic to antiferromagnetic to ferromagnetic. And we've just sort of started that recently. We're going to try to vary the thickness of that spacer layer and look at different materials to see how it affects the dynamics.
I also seem to remember, actually, there was early on, a few years back, there was a report one can see also when you do experiments at the copper edge, you also see some weak magnetic moment.
Those were, to my knowledge, static measurements, and so you get a small induced moment in the copper. So what we would hope to see is, can you see an induced moment in the? One of the things we would be looking for is, can you see a small induced moment in the copper in a dynamic measurement that may actually be slightly larger than what you would have under just static coupling between the copper and the iron, or whatever ferromagnetic material you have in there.
Oh, yes.
Maybe I missed it, but you were talking about placing rare earth materials. Getting the magnetic components. There's a simple explanation why.
Why one can get the performance of rare earth magnets without rare earths? Is that the question?
Yes. What's obviously they're not as good as the heavy rare earth at that point. But
So,
there's something you're going to do to those other non-rare earth materials to try and get you close to it. What's the...
well, that's sort of the main goal of our just started research project. But we've our research consortium has looked at these cobalt carbide nanoparticles, and they've already shown that in very small quantities, they can get a performance that's similar to samarium cobalt without any samarium in there. Now, the reason for that is they really don't understand very well. So the whole process of this project is to first synthesize more material in different ways, to look at that material with the techniques at the beamline, and then to connect that up with theory and first principle calculations of different types of structures that may be able to explain why these things behave like rare earth permanent magnets, but without any rare earths. So it's sort of going to be a feedback cycle of sample production, measurement, connection with the theorists, which will then hopefully inspire new synthesis efforts that will eventually lead to better material. So the short answer is at the moment we don't know. We believe it's connected with the orbital moment in the cobalt, but we don't have those measurements yet.
How would you make large quantities of materials?
So these are done in a chemical synthesis method, a wet chemical synthesis method. And you basically, from what I understand, I'm not the chemist making them, but you essentially just scale up the sort of beaker size material into bigger and bigger vats. So then it becomes kind of a chemical engineering issue more than a synthesis issue. Short answer is they have tried to scale it up. One of the goals of this ARPA-E thing is to actually make what they call compacts out of these materials, and then see if they behave similar to the compacts made out of rare earth material. So they have methods for scaling up. I don't know exactly what they are.
Any other questions?